Time, get ready for that to come to a screeching halt. If things were making sense and then things are clicking along nicely. I hope that I'm only kidding, but a lot of students, as I mentioned in the homework document this week, or in the assignment document this week, say these weeks are the toughest ones that we have. And the reason is we're to the results section of Marie, so that means statistics. And for most of us, that would mean a big yuck. I know that some of you have had a statistics class, many of you have not. My purpose in this lecture and in this class will be to give you enough of an exposure to the types of statistical analyses that you'll see in a study that you should feel pretty confident. And the other thing I'll provide you with is some resources to go to if you say, gosh, I've never heard of that study before, or I didn't have a stats class and I don't know what that is. Throughout the weeks, we've kind of been doing little pieces of this, whether you realize it or not. And now we start into the big chunk. In the results section, we're really looking at the statistical data as it's presented and any adjustments that the researchers may have done in the data. So here we go. When we look at the results of a study for some outcome, and you've already been looking at outcomes last week, we talked about with outcomes, are they precise? Are they accurate? Can they be measured with precision? Now we're going to look at how about the results of a study? Can those be precise? What are the chances they were due to chance alone? And so p-value, if you did your reading and watched your videos like you're supposed to have, you know that p stands for probability. So a probability value tells us about what are the chances that the results that we measured happened by accident. They're due to chance alone. I found some sort of great outcome from a study, but maybe it just happened by chance alone. And you learned that the most common p-value that we use in a medical study to indicate statistical significance is if the p-value is less than 0.05. The other thing that a person has that they are, the author of a study can do to show you the role of chance is to report it as a confidence interval. And more we're seeing confidence intervals repeated. They are the range of plausible results. Rather than saying there's only one possible result, it's 0.05, so it's only 5 out of 100% that it happened by accident. What if you gave me the actual range? And that in most cases is going to be reported as a 95% confidence interval, and in most studies it's going to be just shortened to CI, and they'll expect that you know that means confidence interval. So when the researcher puts together the study, when they want to show you probability or the chances that happen by accident, they could either report that information as a p-value or a confidence interval to help you know what are the chances that this outcome they found, this weight loss in the laparoscopic banding group, happened by accident. If you're given the choice between the two, hopefully by the end of this lecture you're going to know which one you would select to look at. Okay, so the role of chance then. Let's say we're putting together a study and we're going to have two groups in our study. Each of them receives the same intervention, but group A loses 10 pounds and group B loses 3 pounds. So the average weight loss was 7 pounds. If we were reporting a p-value then, we would look only at that information, the 7-pound thing, and we'd come up with a number that represented the p-value. What's the true effect of the weight loss program? Well, not everybody in the study lost 7 pounds. And the p-value would have a tendency to make me think that. And obviously the p-value is not going to be reported as 7 pounds, because if you've done your reading and watched your video, you know that p-values are going to be usually reported as a decimal, or in fact almost always as a decimal. So what is the actual result is probably somewhere in a range, and that's where this 95% confidence interval. It looks at what are the chances that this just happened by accident. And not everybody lost 7 pounds. The true effect is probably best represented somewhere in a range of results. Tell me the highest that somebody lost and tell me the lowest that somebody lost. Then that gives me more information. And this is not just standard deviation. It's coming up with a number that represents where do we think the true amount of weight loss would fall if this study is repeated a number of times. So, for example, if this were published, I might see something like this. The mean or the average weight loss was 10 pounds for patients in one group, and 3 pounds in the control group, and the average was 7 pounds, with a 95% confidence interval of 2 to 12. This 95% confidence interval means that 95% of the time, if this study was repeated multiple times, 95% of the time the true effect would be within the range of 2 to 12 pounds. The p-value would have me think it was only 7 pounds. The confidence interval tells me how precise is the result. Well, it's really 2 to 12 pounds, which is a pretty big difference. If I'm looking at weight loss, I'd be much happier to lose 12 pounds than I would 2. If you only told me the average was 7, you're not really giving me the range to where the results would really fall most of the time, 95% of the time. So another way to say that is, could you put up with, if you went through all this work of whatever this weight loss program is, would you be happy with only 2 pounds weight loss? If you would, then a 95% confidence interval is okay for you. Would you be happy with a 12-pound weight loss? And if you'd be happy with any weight loss in between there, then a 95% confidence interval is acceptable to you. Okay, what would happen if the study were repeated 100 times then? What does the confidence interval tell us? Well, obviously, if we repeated the study 100 times, not every time that we repeat the study is the average weight loss going to be 7 pounds. Because of chance, there will be some studies that if we did all the exact same steps, in some studies patients would lose more than 7 pounds, and some they would lose less. So each one of those studies would have a 95% confidence interval reported. But somewhere, can you see these ones with X's on them? And if you look at how many of these, there are 5. So a 95% confidence interval says the true results of this weight loss study fall somewhere between 2 to 12. And if we repeated this study 100 times, 95%, or multiple times is probably the best way to say it. This one just shows you 100. 95 of the studies fell within that range of 2 to 12. The truth lies somewhere in between that. In 5 of the studies, because we had a confidence interval of 95%, the results would not match what we had as our confidence interval. So a quick way of saying a 95% confidence interval is saying we're 95% confident that the real results of weight loss from this intervention fall somewhere between a range of 2 to 12 pounds. Okay, so here's the real clear definition then. The interval computed from the sample data, so we take the data that's collected, and if the study were repeated multiple times, it would contain the true effect 95% of the time. So confidence intervals are a range. They're a range that tells us if I repeated this study multiple times with 95% accuracy, we can say that the true result, the true effect of this intervention, the results would fall within 95% of the time. So confidence intervals are a measure of how precise an estimated effect is. The range of the confidence interval depends on 2 main things. It depends on the number of observations, and in most cases that's going to be the number of people in a study. This is something that the researcher can control. They can choose how many people they put in a study, and in fact when they sit down to develop a study, they sit down with a statistician and they say, okay, I think we're going to see this much of an effect based on other people's results and similar studies which have dealt with this illness or this medication, or in this case this amount of weight loss. So if we want 90% statistical power, tell us how many people we have to put in each arm of the study. If we want 95% power, tell us how many people we have to put in the study. And the statistician would tell them how many people they need to have in the study. So the pattern between confidence intervals and study power is the larger the number of people in the study, the narrower the confidence interval, the more precise the results become. The smaller the number of people in a study, or the number of observations, if we measure something, the wider the confidence interval is, and the less sure the results are. Okay, the spread in the data is the second thing, and I'm sorry that's showing up there. The spread in the data is the second thing that can affect the confidence interval, and that's something that the statistician, or the researcher really can't control all the time. So what if we repeated the study, and in one time that we repeated the study, the average weight loss in group A was 10 pounds, but the standard deviation was a pound in either way, so we'd have 10 plus or minus 1. In this, we had 3 plus or minus 1 pound. In this study, we had an average of 10, but the standard deviation was plus or minus 5 pounds. And in group B, the average was 3 pounds, but the standard deviation was plus or minus a pound. So I think you could agree this one would have much more precision, and we would have a narrower confidence interval. If all of the data clustered this tightly, it would give us a narrow confidence interval. So what are the ways we could get a narrow confidence interval? We can have a large number of observations or a very small spread in the data. The standard deviation could be really tiny. Then we can be more accurate and precise in saying we feel 95% confidence that the real results are somewhere within this range, and that range would be narrower. If we have fewer numbers of observations or low numbers of participants, then, and it doesn't mean you have to have large numbers of people in a study. Remember, you can have a study powered to 90% and only have 25 people in it. Usually the larger the number of people, the narrower the confidence interval. The smaller the number of people, or the smaller the number of observations, the wider the confidence interval. So the more spread the data is, the larger the standard deviation, the larger the confidence interval is. And what we ultimately would like to see is a small confidence interval. So large number of people is usually a good thing in a study. Small confidence interval is usually a good thing in a person. So a 95% confidence interval is the most common one that's used in medical research. In some cases, you may find a study where they said or reported a 90% confidence interval. And what you're going to see is it may be a p-value and then it says confidence interval was this. Or it may be a relative risk. We're going to talk about relative risk next week. And it may say your relative risk was 1.6, but the confidence interval was -1 to 3. So we'll talk about wide and narrow confidence intervals in reference to specific things as I go through the gastric banding article in just a minute. The higher the degree of confidence, the wider the confidence interval. So if we have a 99% confidence interval, if the researcher decides they want a 99% confidence interval, that it's going to necessarily make, if you want to be 99% confident that the real results, if the study is repeated multiple times, falls somewhere in that range, it's going to have to be wider than if you'll settle for lower confidence interval. So what if you only want to be 50% confident that the actual result or the actual outcome lays somewhere within a range of data? Well, if I only want 50% accuracy, then my confidence interval could be narrower, because you're only having to be right 50% of the time instead of 95% of the time. So relationship between confidence intervals and p-values, there is one. Even though if I might see a study that reports one or the other, if there is a confidence interval reported, it actually tells me about the p-value. And I'll show you that right here for one thing, and I'll show you in the gastric banding study. Let's say that study reported the confidence interval of 2 to 12 pounds for that 7-pound difference. So they said average weight loss was 7 pounds with a 95% confidence interval of 2 to 12 pounds. So the p-value for that would be less than 0.05, because the reason that this did not include the value of 0. We're doing a simple math calculation. 7 pounds was the average, and the real result went from 2 to 12 pounds. Because this did not include the value of no effect, which in this case would be 0, we can infer that the p-value is less than 0.05. So a confidence interval when we're doing math that does not involve a zero, if we're just doing simple subtraction like this weight loss one, then that's another way to say the p-value is statistically significant. And in most studies, we said the statistical significant level for p-value was 0.05. Alternately, what if they said the confidence interval was -3 to 17 pounds? The real, with 95% confidence, they say that the real result falls somewhere between -3 to 17 pounds. Well, because we're doing math, and because this value includes 0, the p-value would have to be greater than 0.05. So this confidence interval, because it includes 0, is another way to tell me the data was not statistically significant. If the confidence interval is exactly like a 0, then the p-value is exactly 0.05. So if the confidence interval is at the point of no difference, then we know the p-value is exactly 0.05. So look at this one. Do you see how this is the actual value? In this case, it would be the weight loss. So here's the 7 pounds, and this one is showing the -3 up to the 12. And this is the line of no difference, which when we're doing simple math would be a value of 0. In this case, it's showing, because this crosses the line, that confidence interval is what's shown here. Here's the mean, represented by this box. Here's the confidence interval, and we're going to do more with this next week when we look at forest plots. Here's the mean for this one, and here's the confidence interval. This confidence interval is narrower. That's a good thing. This confidence interval does not include the line of no difference or no effect. Another way to say this is, without even looking at the numbers, I know the confidence interval did not include 0. I do know this confidence interval included 0. They're showing it graphically to me. Therefore, if the confidence interval of a simple subtraction problem includes a 0, if it passes that range of 0, if the range includes 0, I would know that the p-value is greater than 0.05. It's not statistically significant. If the confidence interval range does not cross the line of no effect or no difference, the p-value must be statistically significant. And if it would have ended right here, then I would know that the p-value was exactly 0.05. So again, this was the mean. Here's my confidence interval represented graphically. So the value for no difference or no effect, if I'm just doing simple math or subtraction, the value of no difference is 0. When the effect measures a ratio, and next week we're going to talk about risk ratios or odds ratios. When you do a ratio, the way that we show there's no effect is it would be 1. If I compare two things and they're both equal, 10 divided by 10, the value is 1. So if it involves a ratio, the value of no difference is 1. So if I go back to this picture, notice it didn't put a value for no difference between the groups, because it would depend on, are you doing simple math, and then the value for no difference would be 0. Are you doing a ratio, then the value for no difference would be 1. So pay careful attention to what's being evaluated to report the confidence interval. If it's just simple math, look to see if it includes the value 0, which would be the line of no effect. So when given the choice, what should I choose? I hope you would pick confidence intervals. Confidence intervals still have a problem. They don't tell me exactly about precision, but they give me more information about it. So p-values and 95% confidence intervals are related. But confidence intervals are preferred because they tell me information about the range of plausible effects. In other words, it tells me something about how precise the estimate of the effect is. And that's a valuable dimension that p-values alone do not tell me. And remember, if I have the confidence interval, I can easily infer whether the p-value is statistically significant or not, depending on, does it include the value, does the range include the value of no effect? The problem with both of these, confidence intervals and p-values, is they do not answer a critical question. Two critical questions. One, is the result correct? To answer that question, that's what you're going to have to look at, the data. You're going to look at the data and see if there's the possibility of bias. We've talked about bias in the last week. So is there maybe bias that's influencing the results? The second thing is that confidence intervals and p-values don't really tell me anything about whether the observed effect is important. So we can find something out that's statistically significant, but I say, you know what, that's really not important to me or the patients that I care for. And so to answer the second question is where you have to rely on your own clinical judgment. So the bottom line, if you were doing a PICO study and the patient came to you and said, I looked at this study result, or I want to participate in this weight loss intervention program, you looked at the data as my healthcare provider, do you think it's worth it to me? And that's where I'd ask the question, would it be worth it to you to lose 12 pounds? Would it be worth it to you to lose 2 pounds? If the answer is yes, well, with 95% accuracy, or I guess I shouldn't say 95% accuracy, it should be that I'm 95% confident that if the results were reported multiple times, 95% of the time, the real result would fall somewhere between that 2 to 12 pound range. If that's not acceptable to you, then the observed effect, no matter whether it was statistically significant or not, is not important.
Students, this video probably looked a little bit different. What I did was figure out a way to be in 2 places at once. Isn't that amazing? I recorded a recording that was already done in one format to put it in this new format. And so I hope that you find the information helpful. And with that, I will end this recording.